Welcome back. Today we're going to talk about optimal control and dynamic programming. All right. In particular, we're going to start off just by kind of outlining a nice basic class of optimal control problems. After this, we'll talk about an algorithm for solving a special subclass of these problems. So this algorithm is called dynamic programming. And then we're going to finish up by talking about the HJB equation, which is kind of a continuous time analog of these discrete time optimal control ideas. Okay, let's get started. So first off, I want to start by talking about optimal control problems. Okay. So what are optimal control problems and where do they kind of arise? Well, let's kind of think about what we've done so far in the course. So far, what we've done is we've shown how to find simple stabilizing control laws, right? For example, I told you last time that you could find a control law u equals k times x that stabilizes your system, provided your system is stabilizable, or you could do something with output feedback plus an observer to stabilize your system, right? The list kind of goes on. But, all that we did so far is we just considered methods for designing a controller. Okay? So we said nothing about the best controller possible. Best controller. Okay. So this business of kind of figuring out what the best possible controller for your system is, given some sort of design criteria or some kind of actual nice specification of what best means, this is the business of optimal control. Okay? So basically, the idea of optimal control is you pose the control design problem as an optimization problem. Okay? And then using some sort of technique, you'll solve the optimization problem to get the best control law, okay, for this particular optimization. All right, so that's the kind of general high-level idea of what optimal control is. We're now, instead of just saying, okay, I want to stabilize my system, maybe we're saying, I want to stabilize my system subject to my control law being the best according to this criterion, okay? So something along these lines. Okay, so let's kind of start to put a little bit of math down towards these ideas. Then let's figure out what is needed. What is needed to actually pose one of these optimal control problems? To pose an OCP, optimal control problem, as I'll usually abbreviate it. Okay, so what I'll do is I'll consider this kind of simple example where, we have some sort of nice racetrack over here, and it's a very complicated racetrack. Here's our start line, and let's say we have a little car over here which we're trying to control around a racetrack. Okay, so let's get the car around the racetrack. So how could we set this up as an optimal control problem? Well, maybe what I want to do is I want to figure out a control law that best balances the fuel consumption and the lap time. Okay, so this is, pretty reasonable. Maybe if I'm doing a long race, right, I want to kind of make sure that I get to the end. So it's important that, I don't use up all of my fuel at once. And lap time because I want to do well in this race as well, right? I want to kind of get around there quickly. So what do I actually need, mathematically speaking, to set up this optimal control problem, right? Where I could set up an optimization problem that says, okay, the solution to this optimization gives you the input that best balances fuel consumption and lap time. Well, first, I kind of need to specify the basic setting for this problem, right? So what I need, very, very basic setting, is a dynamical system, right? D, which is representing the car. All right. And maybe I have some time interval t0, t1, which is a subset of my time set, on which I'm interested in performing the optimization. Okay, so, just for the sake of this lecture, for simplicity, we're only going to consider kind of these finite bounded time intervals, but you could do this on arbitrarily long time intervals as well. Okay, this is our basic setup, what's kind of in the background, right? Now, what else do we need? Well, I kind of keep mentioning that, we have some sort of best criterion that tells us, very precisely whether one sort of trajectory or input is better than another, right? So what else do I need? I need something that tells me whether one control law is better than another. Okay? So here's the basic idea. What I'll do is I'll define some function that assigns a real number called a cost to each input signal and trajectory on the interval t0, t1. Okay? So this function, which I'll call j, will take in a trajectory, which is produced by an input signal u, and it will tell me how costly the pair of u and resulting trajectory x is. Okay? So this function is called a cost function, as the name cost might suggest. And basically what this cost function is doing is it's telling me, okay, if I take this trajectory, how much will this cost me? If I take this trajectory, how much will this cost me? So on and so forth, right? So the main idea, what we want to do, is we want to minimize the cost. Minimize the cost. Okay? So our goal in our optimal control problem, is to solve the minimization min of j of x, comma u, such that x is the trajectory resulting from u, and such that u belongs to, let's say, the input space of my dynamical system. Okay? This is kind of like a very basic general framework for these optimal control problems. Okay? So, for example, if I'm to go ahead and draw one given trajectory over here, which results from one input, and then I draw another, each of these will have different costs, right? And this function j will tell me exactly what the cost of the red trajectory is and what the cost of the blue trajectory is. And kind of by performing an optimization over all these possible trajectory and input pairs, I can figure out the best one, the one that solves my optimal control problem. Okay. So this is kind of a basic framework, right? We need a dynamical system, we need a time interval, and we need a cost function, which actually specifically tells us what trajectory is good and what trajectory is bad. Let's kind of go ahead and put these all together into just a nice formal definition that tells us what an optimal control problem actually is. Okay? So we're going to define something called a finite horizon optimal control problem. Which just kind of abstracts these ideas from this simple car example away. So definition, finite horizon optimal control problem. Okay. So we say that a finite horizon optimal control problem for a system d equals u, y, sigma, phi, r. This is just one of our abstract dynamical systems on a time set t is specified by the following information. So first we have a time interval. Okay, so this is going to be a bounded interval. Bounded interval t0, t1, which is a subset of t, on which the optimal control problem is defined. Okay, so this is kind of our time interval of interest. On t0, t1, we're figuring out what to best do with our system. Okay, Now, second, just to ensure that this problem is well posed, we're going to specify an initial condition. Initial condition, right? That just tells me where my system is starting. It's going to be a value x naught in my state space sigma, where the system is at time t naught, all right? And then third, we're going to specify our cost function, right? And this is going to be a map, j, which is going to take in a state as its first argument, excuse me, a state trajectory as its first argument, and an input trajectory as its second argument. So this is taking in a state trajectory on the interval t0, t1, going to sigma, and an input, right, u, which will go from t0, t1 to my input value space, and returning a cost, which I'll call j of x, u, which belongs to the positive real numbers or non-negative real numbers and can potentially be infinite. Okay? So I'll talk about the reason for adding infinity in just a moment. All right? Just kind of keep it in the back of your mind for now. All right, so what's our goal of this finite horizon optimal control problem? Well, the problem itself is the minimization infimum over u belongs to my input signal space u of j of phi of my signal t naught x naught u. And this will be restricted to the interval t naught t1, as well as this input signal u restricted to the interval t naught t1, like this. Okay, so our goal is effectively saying, all right, I'm giving you this cost function, I'm giving you a dynamical system with some input signal space. Now what I want to do is I want to minimize the cost function, right, which will be a function of the trajectory of my system, right, on the interval t naught t1, and a function of the input signal on this interval t naught t1. I want to find this input signal that gives me the lowest possible cost. Okay. Just as a quick side note, Mark, the restriction notation, which I have here, t naught t1, will be implicit in the future. Okay? So it's something you want to kind of include if you want this to be formally well posed, right? Because we do actually want to pass our system a signal that's defined on t naught t1, not something that's defined on all of t. But, we don't lose a whole lot mathematically if we just don't write it, okay? So usually I'll just write it without this restriction. Okay, so I mentioned above that, we're allowing our cost to take on infinite value, right? Why is that? So question, what's the point of infinite cost? Well, something that you might notice, right, is that this problem is entirely unconstrained, right? As written, we haven't written anything like the state needs to belong to this certain set, or maybe the input needs to belong to an even smaller set, anything like this, right? We just said we have a single cost function which depends on our state trajectory and on our input, right? So what this infinite cost kind of gives us the ability to do is it lets us add in constraints to our optimization problem. So let's consider the example of the car. So for example, I want the car to stay on the track. Okay, let's say I represent the track by a set xt, which is a subset of my state space. How can I encode this hard constraint that I want my state to remain in this set for all time in my optimization problem? Well, there's two ways of doing it, right? One of them is to write my optimization problem as a constrained optimization, inf over u and u, of j of phi, t naught, x naught, u. Again, I'll just go ahead and suppress this restriction notation. Will also depend on u. and this will be subject to the constraint that phi of t, t naught, x naught u will belong to the set xt, should hold for all t in t naught t1, right? So this is writing it as a constrained optimization problem, right? Or I could actually rewrite this as an unconstrained optimization problem taking advantage of this infinite cost, okay? So what I'll do instead is I could define jxt as the function which takes in a trajectory, right? And it returns infinity if there exists a time in t naught t1 such that x of t is not in my set xt, right? And then just return 0 otherwise, okay? So what this does is that if we go ahead and now write our optimization problem as the unconstrained problem, inf over u and u of j of phi, t naught, x naught u, u. Now we add on this potentially infinite cost, jxt of phi. Then what we find is that, this problem over here that we've just written, kind of incorporating this new infinite cost term, is actually equivalent to the problem we expressed above, okay? Because in order to minimize this, well, we're probably looking for a finite cost, right? And if we break this constraint, there's no way we'll be able to have a finite cost, okay? So any trajectory that breaks this constraint is automatically non-optimal, which means that we end up actually getting the same optimization problem as what we had posed above, okay? So this is just kind of the generic reason for why we allow infinite cost. In the rest of the lecture, this won't be a huge concern for us, okay? Okay, so with this in mind, let's kind of define what it means for one of these optimal control problems to actually be solvable, okay? So what does it mean for an optimal control problem to be solvable? Well, kind of in optimization speak, we tend not to use the language solvable, rather we use the term feasible, okay? So let's go ahead and define what a feasible set is for one of these optimal control problems. Now, after we've done this, we'll define what it means for the problem itself to be feasible, okay? Let's go ahead and say definition. This is going to be feasible set slash feasible problem. So let's go ahead and consider one of these finite horizon optimal control problems. So consider a finite horizon optimal control problem. Then the set, which I'll call FOCP, it's defined as the set of all input signals in my input signal space such that j of phi, t naught, x naught, u, my input signal u, is less than infinity, is called the feasible set. Feasible set of the optimal control problem, okay? So basically what we're going to say is that if FOCP is non-empty, then the problem is said to be feasible, okay? And then otherwise, if FOCP is empty, the problem is infeasible. All right, so basically what we're saying is that the problem is called feasible if there exists an input in our input signal space that actually goes ahead and gives us finite cost, okay? Now, if we always have infinite cost, then there's not really anything we could say about the minimization, so we say that the problem is infeasible, all right? So just as a quick example, infeasibility might arise if we put two conflicting constraints on our problem, right? So if we have two constraints that directly contradict each other, and then we try to put them in the objective function like we did up here, then we'll find that we always have infinite cost, right? Because either one of them is going to be infinite for all potential values of our input. Okay, so that's what it means for the problem to be feasible, all right? Now I want to talk about what it means to actually solve this optimal control problem. So what is a solution to an optimal control problem? Well, kind of when we mention this word solution, there's a couple of different things that could come to mind, right? First, we could have the value of the infimum. Okay, so, actually what this infimum inf over u and u of j is equal to, right? That's one potential candidate definition for a solution, right? What else could we have? Well, we could have an input signal, u, which achieves the supremum, infimum. Okay, so, that might be a solution to our optimal control problem. Third, we might be interested in the trajectory, x, which corresponds to an input, u achieving the infimum, right? That might also be of interest. And finally, 4, which will be what we'll focus on for kind of the remainder of this lecture in just a few minutes, will be an optimal control law, which is going to be a feedback law, okay, which goes from my state space cross with 0, t into u, that always achieves the infimum. Okay, so these are 4 kind of loose ideas for what we might want to look for when we're actually solving an optimal control problem, right? Maybe we're just interested in the optimal value, right, which is the value of the infimum. Maybe we're not interested in the optimal value, but rather we're interested in an input signal, which achieves that value. Okay, maybe we're more interested in the trajectory, or finally, point 4, which is what we're going to focus on today. Maybe we're interested not in the solution to, an optimal control problem for a single state, right, for a single initial condition, but rather maybe we're interested in finding a closed-loop optimal control law that solved this problem across the entire state space. Okay, so let's just go ahead and put some formal definitions down to each of these, and then we'll start talking a little bit more in detail about how we obtain each one of these. Okay, so let's set out definition, which will be optimal cost / solution / trajectory / control law. Okay, so what we'll say is consider a finite horizon optimal control problem on an interval t0, t1. Okay, so first let's go ahead and define something called the optimal cost function, right? So, optimal cost function. So what this is going to be is it's going to be a map from my state space to the reals, including infinity, that just returns the optimal value of the infimum given any given initial condition. Okay? So, the optimal cost function is the map J, which goes from my state space sigma, and maps into r greater than or equal to 0, union infinity, right? So it can take on an infinite value, and this is defined such that, oops, I'm missing a star over here, j star of x0 is equal to the infimum over u and u of j of phi of my signal t0, x0, u, u. Okay? So what this is equal to is just directly equal to the actual value of the infimum for a given initial condition. Okay? Let me just make this extra clear that this is a signal. Okay. So that's the optimal cost function, right? It takes in my initial condition and it returns the optimal value of the problem for any initial condition. What else do we have? Well, 2. By convention, we call any input signal that achieves this an optimal solution. Okay? That gives us 2, which is optimal solution. So we say that a signal u, which belongs to my input space u, is an optimal solution for the initial condition x0 if we have the following. If we have j star of x0 is actually equal to j of phi t0 x0 u. Okay? So if this input signal achieves the infimum, we call it an optimal solution of the optimal control problem for the initial condition x naught. Okay, what else do we have? Well, above we also mentioned an optimal trajectory, right? So optimal trajectory is going to be our next term of interest. So we have that a map x going from t naught t1 to sigma is an optimal trajectory corresponding to optimal solution u for x naught if we simply have x of t is equal to phi of t, t naught, x naught u for all t belonging to t naught, t. Okay, so the optimal trajectory corresponding to a given optimal solution is simply the state trajectory that just results from plugging in that input signal. Okay? All right. And finally, we have an optimal control law. All right, lots of optimality, my gosh. All right, so an optimal control law is a map, K star, which goes from my state space sigma crossed with this time interval, t naught t1, on which my system's defined, right? And it maps to my input space u, so this is the input value space, right? And it satisfies, for all x naught in sigma, there exists an optimal input signal, or an optimal solution, which I'll call u x naught for x naught, such that k star of phi of t, t naught, x naught with this input signal, u x naught, evaluated at t, is equal to u x naught at t for all t and t naught t1. Okay? So effectively, an optimal control law is just a map of the state that returns an optimal solution. Okay? So instead of just being a function of time, it's an actual function of state. So it tells me for any state in my state space, this is going to be the optimal control to apply at this particular state. Okay, fantastic. So these are our four main kind of optimal pieces of interest, right? Whenever we frame an optimal control problem, typically we'll kind of find ourselves wanting to find at least one of these. But as I mentioned earlier, our main goal in this lecture, and kind of the strongest one out of this bunch, is to find an optimal control law. Okay? This is quite hard to do, right? So we have to solve this really big optimization problem, and if we're looking for an optimal control law, right, it's not good enough just to solve it for one initial condition. It kind of looks like we need to solve it for every initial condition, right, and kind of figure out this nice function of state that actually tells us what control we should be applying. So this is a, pretty challenging task, all right? So my question is, how do we develop general techniques for identifying optimal control laws? Right? For problems that are kind of this nature, it's really nice to have sort of general theorems that we can kind of rely on to kind of make some progress on these problems, right? But the kind of issue with this is that the current class of problem, right, these finite horizon optimal control problems, which we've considered, are extremely general, right? The cost can blow up to infinity because I can specify any sort of constraint that I want. My cost function is arbitrary. The system itself doesn't really have any structure. So there's not really a whole lot that we can say, okay? So currently, our optimal control problems, in general, are too unstructured to make good progress in this direction. Okay? So what I'm going to do is I'm going to add a little bit more structure to both the system and to the cost function, and then we'll kind of see how we could develop some general techniques that kind of fall out naturally from these. So what structure are we going to add? Well, there's some kind of classic structure that we always like to add, right? So first what we could do is we could specify that our system be linear and time invariant, right? So for example, we could have that it's governed by xk plus 1 equals axk plus buk, where we're drawing the uk from some set u, which is a subset of Rm, right? Likewise, we could do something like x dot of t equals ax of t plus bu of t, okay? This adds a lot of structure to the state transition map, right? This is kind of a recurring theme that we've seen across the course. What else can we do? Well, what we could do is we could add structure to the cost function, okay? So maybe at first it's kind of non-obvious why this would help, but we'll see this is actually essential to being able to make good progress on finding general techniques for solving optimal control problems, okay? So to kind of imagine what structure we might want our cost function to have, let's go back to this example of the car, okay? So let's turn back to the car, okay? So let's suppose it's a discrete time system for simplicity. What structure might we want our cost function in this case to have? Well, I'll just kind of give you a moment to maybe think about what the cost might look like if we're trying to balance both fuel consumption and lap time. Okay? Just take a moment to give that some thought. All right, so I'll assume you've kind of given this some basic thought. So let's kind of sketch out what our cost function for this system might actually be. So let's say, suppose we take the interval 0, n for our system, okay? This is going to be the kind of basic setup for our optimal control problem. So we're taking a time interval 0, n, which is a subset of the integers, and let's say also we fix some initial condition, okay? Now, what sort of structure should our cost function be? Well, one idea is that at each time step k, which belongs to this interval 0, n, we accumulate some cost, right? So maybe at each time step, right, since I'm deciding my inputs time step by time step, if I use a lot of fuel, or if I take a really, really high acceleration in one particular time step, that's probably going to be bad, right? So it kind of makes sense that we want to be accumulating cost as we go along, right? That way we can really kind of zoom in and make sure we're taking the right actions at every step along the way, okay? So let's say at each step we accumulate some cost, which I'll call g, which is a function of the car position at k, the input to the car at k, and let's just say for generality the time step k itself. Okay, maybe we care more about actions that are taken sooner rather than later, right? So it could depend on the time step as well. Okay, so we're accumulating costs at each step, right? K belongs to 0, n minus 1. Let's actually do this as n minus 1 since we won't have an input all the way in our last step, right? Now, at our final step, let's add on a cost to account for our final position. Okay? So let's say all the way at the end, we kind of care about what we're going to be at, right? So let's add on a cost gn of position at time step n. Okay? So if we go ahead and we add together all of these accumulated costs together with this cost at the final position, we'll find that our cost function will be of the form gn of position at time n plus the sum from k equals 0 up until n minus 1 of g of position at time k, input at time k, and then the time k itself. Okay? So we kind of accumulate these. as time goes on, right? Because at each step, we're interested in kind of measuring the cost of each action that we're taking, okay? So it turns out for discrete time systems, this structure of taking a sum over these accumulated costs as we're going along is kind of a structure that's really, really common, okay? So we can really express a lot of interesting things with cost functions of this form. All right, so what we're going to do now is we're basically going to put a cost function of this form together with a linear time invariance system, right? A discrete time LTI system. And we're going to declare that to be kind of a more specific class of optimal control problems of interest, okay? This brings us to the definition, which is a discrete time. I'm going to call it a basic linear optimal control problem. Okay, so put basic in quotes here. So a discrete time, basic linear optimal control problem is a finite horizon optimal control problem where the following is true. So first, our system is a discrete time LTI system representation A, B, C, comma, D, in which my state space sigma equals Rn. My input value space U will be a subset of Rm, as opposed to just being all of Rm like it usually is. And finally, my input signal space will be the collection of all sequences, U, which go from Z into my input value space U, which is a subset of Rm. Okay? So I'm just taking this, special subset of Rm, which I'm calling U, just so we get a little bit more flexibility in terms of our definition of this problem, okay? All right, so that's our system. What else do we have? Well, we also need to specify an interval, right? An interval. So the interval is of the form 0, n, which is a subset of the integer 0, where n is a positive integer called the horizon, okay? So in optimal control, we commonly use this word horizon just to refer to the length of the optimal control problem, okay? So that's all that we're doing here. All right, so we've specified the system, we've specified the interval. Now I just want to go ahead and specify the cost, right? And the cost function will take this special form of this accumulated cost that we specified above, okay? So the cost function will be j of trajectory x and an input signal u will be equal to gn of xn plus the sum going from k equals 0 up until n minus 1 of g of xk, uk, and then k, okay? Where gn is called the terminal cost, okay, because it's the cost that penalizes the final state, right, the terminal state of our optimal control problem, and G is called the stage cost, okay, because it's the cost that's associated with each stage of the optimal control problem. All right, so if we put all these different factors together, what does one of these problems look like? Well, there's a common form in which these problems are written out that I'll kind of show you now, okay? These problems are typically written in the following form. So we'll have an infimum over a sequence of u, right, which I'll write as u going from time step 0 up until time step n minus 1. So this sequence will be a subset, of u, which itself is a subset of Rm. Now we'll have a sequence of states, x, which goes from 0 up until time n, right? This is a subset of my state space Rn. And what we're going to be taking the minimum of, or infimum of, will be gn of xn plus the sum going from k equals 0 up until n minus 1, g of xk, uk, k. These will be subject to the constraints. We usually write st for subject to or such that. It's really a matter of personal preference. Subject to the constraints, x at time k plus 1 equals a x at time k plus b u at time k, where k belongs to the interval 0 up until n minus 1. And then we'll also have a constraint of our initial condition, right? X at time 0 equals some x naught, where x naught has been provided to us just as a part of the definition of this finite horizon optimal control problem, okay? So this is kind of the standard formulation. Okay? So I know this does look a little bit different to what we had talked about before, right? Earlier when we were defining one of these kind of general finite horizon optimal control problems, we'd said that you really just go ahead and you plug your state transition map directly into the cost function, right? Now, I'm sure you can see why that might not be the most transparent thing for our problem, right? It turns out that, now that we have this kind of nice structure, our problem's a little bit easier to read, and we can kind of tell what's going on a little bit easier if we kind of expand it in this extra form, okay? So what we've done here is, instead of working directly with the state transition map, we've introduced these new variables, x, right, which really directly deal with my state, and I've just added in this constraint that, this x trajectory needs to exactly equal what the state transition would be, all right? So this is just a basic kind of reformulation, which is a little bit easier on the eyes. All right, fantastic. So I just want to make one clarifying remark, which I mentioned earlier. When I write u going from 0 up until n minus 1, what I'm referring to is the sequence u of 0 all the way up until un minus 1. Okay? All right, fantastic. So this gives us a really nice kind of workable form for a discrete time linear optimal control problem, right? This is already looking a lot friendlier than what we had above, right? This is going to be the first class of optimal control problem which we're interested in developing general techniques to solve for in today's lecture. So what else do we have? We've done this for discrete time, right? What does the continuous time case look like? Well, it turns out continuous time optimal control is really hard, okay? Really hard. To really give it a rigorous treatment requires a lot of math and kind of a big digression into some measure theory concerns, okay? So just to kind of avoid this, I'm going to add a couple of extra regularity constraints that just make sure these problems are a little bit easier for us to work with, okay? I'll kind of discuss those as we're going along. You should just bear in mind this is not the most general form for a linear optimal control problem, okay? Hence the name basic in the definition. All right. So with that said, let me go ahead and define a continuous time basic linear optimal control problem. Okay. So continuous time basic linear optimal control problem is specified, let me just say first, is a finite horizon, there we go, optimal control problem, which is specified by the following. First, our system. So our system will be a continuous time, LTI, system representation, A, B, C, D, where sigma will be equal to Rn, right? I have a state space of Rn, an input value space of U, which is a subset of Rm, and finally my input signal space, which I'll just write out in full, which is this cursive U is equal to the set of signals U, which are piecewise continuous from R into Rm, and satisfy U of t belongs to U for all t. Okay? So these are just piecewise continuous functions which take values in this special set U, which I've defined. All right, so there's a little bit different to our general case. We've now added this input constraint just to make these problems a little bit more relevant to what you might see in practice, okay? All right, so that's the system. Next, we'll go ahead and define the interval. Right, so this should all be looking fairly familiar from the discrete time case. So the interval we're going to say is going to be of the form 0, t, subset of R, where t greater than 0 is a real number called the horizon, okay? So once again, the horizon is just the length of the interval, all right? It's just how far into the future we're interested in performing our optimization, all right? So finally, our cost function how are we going to define accumulated cost in the continuous time case? Well, if we're using sums to kind of accumulate cost in the discrete time case, then it makes sense that for continuous time, we can accumulate cost using an integral, right? That's exactly what we're going to do, okay? So the cost function is going to be the following. J of x, u, so it takes in an x trajectory and a u trajectory. I'm going to assume that these are, integrable. You could kind of make of that what you will, but effectively these functions will be sufficiently regular such that they won't have any problems with Riemann integrals, right? So equal to gt of x at time t. So we have a terminal cost term, right? Same as before, plus now an integral from 0 up until time t of g of x of tau, u of tau, tau, d tau, okay? This is going to be my cost. And here, my stage cost, g, and my terminal cost, gt, will be continuously differentiable. This will just make the problem nice and easy for us, okay? So this is for gt, a continuously differentiable function, which I'll write as c1 for once continuously differentiable. It's going to go from Rn into r greater than or equal to 0, and then g will be continuously differentiable, c1 going from Rn for my state, cross Rm for my input, cross r for my time, into r greater than or equal to 0. Okay? So these are once again called the terminal cost and then the stage cost terms. All right, fantastic. So what we had done above, right, is we had kind of posed the standard form for one of these discrete time basic optimal control problems. Now I just want to do the same thing for continuous time, okay? So the standard form will be the following. So now we're going to take an infimum over an input signal belonging to my input signal space u. I'm going to take an infimum over a trajectory, which belongs to at least the set of continuous functions going from r into Rn. And I'm going to minimize my cost function, which is accumulated g of x of t plus 0 up until t, my stage cost, g of x of tau, u of tau, tau, d tau. And finally, these will be subject to the constraints x dot of t is equal to ax of t plus bu of t. And this needs to hold at all t in 0, t, where u is continuous, right? So you might remember from a long while ago in the course, we said that these derivative conditions, when we only assume piecewise continuous inputs, the derivative only actually needs to hold where the input signal is continuous, right? Otherwise, you end up with problems where your derivatives have jump discontinuities, and you can show that's actually a contradiction, okay? So we just specified that this needs to hold at times where our input signal is continuous, all right? Okay, so that's our first part. And then secondly, we'll just specify our initial condition, x of 0 equals x naught, where x naught has just been provided as, a part of one of these finite horizon optimal control problems. Okay, so this is the standard form, right? We're optimizing over a input, u, which belongs to u, and a trajectory, which is a continuous function satisfying the differential equation. And what we want to do is we want to minimize this integral accumulated cost function. All right? Okay. This is kind of the standard form of our basic continuous time linear optimal control problem. So just as a quick remark, I'll suppress the for all t at which u is continuous going forward. Okay? Just because, it's kind of a minor technical detail that we're not going to focus on too much, since we're not going to be hugely formal in our treatment of optimal control, right? After all, we're not an optimal control class. All right, nice. So now that this is said, right, we kind of have our two nice kind of basic structures for dealing with optimal control problems in this linear setting, okay? So what we've done is we've added the structure of LTI dynamics and accumulated cost to our kind of abstract formulation that we had talked about above, all right? So what are we going to do now? Well, now that we've determined this kind of basic structure for an optimal control problem, we could see if we could make some progress on developing general techniques for solutions, right? That's what we're going to do next. All right, so we're now in a good place to start discussing dynamic programming. Okay, so this brings us to our second part of the lecture on dynamic programming. Okay, so once again, we've kind of said now we have this nice basic structure for our optimal control problem. Let's kind of take a crack at seeing if we could, develop a nice solution technique for one of these problems. All right. So what we'll do is we'll start by analyzing the discrete time case. Okay. So we'll consider a basic discrete time optimal control problem. We want to minimize over the sequence u going from 0 up until n minus 1, x going from 0 up until n of gn of xn plus the sum k goes to 0, n minus 1, g of xk, uk, okay, and this is subject to xk plus 1 equals axk plus buk, right? This needs to hold for all k, and subject to the condition x of 0 equals sum x naught, okay? So even though this is a big improvement over what we had before, this is still a really hard problem. A hard problem to solve. Okay? So if we're to solve this problem straight up, right, if I, just kind of give you one of these problems and I say, okay, go find the solution, do it analytically, and do it right now, you probably wouldn't be able to, right? I mean, these functions aren't convex, right, which is a class which is generally nice for optimization. These constraints could be really messy because we haven't assumed any nice diagonal or simple structure on A and B and so on and so forth. There's a lot of factors that make this problem really tricky, right? The principle among these is that this is, kind of zoomed out for a moment there. So this is a hard, multi-stage, dynamic optimization problem. Okay, so we actually have our dynamics, xk plus 1 equals axk plus buk, embedded directly in this optimization problem, right? That's one of the things that's making this really challenging to solve, right? We're doing this optimization over this entire input sequence, right, which could be really big, right? This horizon could be super long, subject to these somewhat complicated dynamic constraints, okay? So what our goal is let's break up our problem into a sequence of simpler problems, okay? Each of which involves only one variable, okay? This way we can kind of eliminate this dynamic, kind of problem, and we can just kind of focus on solving a single static optimization problem, right, where dynamics aren't playing a huge role. All right, so one of our goals, and what we want to do is we want to solve for an optimal control law in each simpler problem. Okay? Maybe by piecing together these optimal control laws for each simpler problem, we could kind of reconstruct an optimal control law for our original problem. All right? So what we want to do is we want to take this really complicated multi-stage problem and just kind of split it up into some easier ones that are kind of more tractable. All right? So what are we going to do? How are we going to perform this split? Well, let's just kind of start by splitting our problem into two halves. All right? I'll just kind of pick some integer m, which belongs to 0 up until time n, and I'll just say, okay, I'll just kind of split it along that line, right? Let's see what happens when we do this. So what I'll do is I'll pick an integer, which I'll call m, which belongs to 0 up until time m, okay? So let's go ahead and split our cost function into the cost before time m and the cost after time m. All right. So what we could do is we can go ahead and we could rewrite our cost, j of x, u, just for arbitrary signals x and u. We can go ahead and rewrite this as the cost which is incurred before time m, right? Which will be this term k equals 0 up until m minus 1, g of x of k, u of k, k. Okay, so this is the cost incurred before time m, and we can go ahead and add the cost that's incurred after time m. Okay, so let me put this in brackets. This is going to be plus gn of, my terminal cost, right? Because my terminal cost happens after time m, plus the sum going from k equals m up until n minus 1 of g of x of k, u of k, k, right? Close brackets. So this is the cost at and after time m. Okay? So if we're trying to split up our problem into pieces, what can we do? Well, something interesting that we notice, right? So we notice is that the cost after time m appears to have a similar structure to the full cost function. Okay? Cost function. So, we kind of notice that we have this terminal cost term, right? And then we have the sum, which goes from k equals m up until n minus 1, right? Kind of all that changes is the lower index of this sum, right? If we started this at 0, then we would exactly get our cost for our original problem, right? So this kind of maybe gives us a hint that if we study this kind of cost after time m, which is a smaller, maybe easier problem to solve, right? Maybe we can make some progress on solving our original problem, right? So let's focus on this, I'll call it cost to go after time m. Okay? So let's say for a moment, since this problem is easier, let's imagine that we were actually able to solve this easier problem. Okay? So let's say, suppose we could solve the easier problem, inf over u going from time m up until n minus 1, x going from m up until time n of gn of xn plus sum going from k equals m up until n minus 1, and then g of the usual arguments, right? It's going to be subject to xk plus 1 equals axk plus buk. And let's just say x at time m is just equal to some value x, okay? So let's say we could solve this for all x, okay? So we get a solution, which I'll call k to go, all right? Let's say that my solution, k to go, is such that for all possible states, for all x in Rn, I have that k to go of, let's say, x in time k is optimal for k equals, let's say, m all the way until time n minus 1. Okay? So I'm able to find some sort of optimal control law. Let me just clarify, that's a big capital K to go. I'm able to find some optimal control law that actually solves this problem for all of my states. Okay? Maybe this is something we could do because the problem's a little easier, right? So how does this optimal control law relate to my optimal control law for the original problem? So how does K to go relate to the optimal control for the full problem? Take a moment to think about, whether you could figure out some sort of relationship between these two. Okay? All right, so I'll assume you've given some thought to this relationship between K to go and the existence of an optimal control law for the full problem. Here's what we're going to say. It's a really nice idea, which is if we have an optimal control law for our full problem, that control law must be optimal for the to-go problem. Okay? So this is a really powerful idea called the principle of optimality. Okay? So if, say, I'm able to find some controller K, which, is a closed-loop feedback controller that gives me the optimal solution to my original problem, then what this principle of optimality claims is that optimal controller for the full problem needs to be optimal for every single one of these to-go problems, okay? So for every single one of these smaller problems. And what's the reason for this? The basic reason is that if an optimal control law, K, for my full problem is not optimal for a to-go problem, then what I would do is I would just switch to my to-go controller once I get there. Okay, I could switch to K to go once I get to step M and get a better cost. Okay. So the basic idea is that, this principle of optimality says, okay, if I want to find an optimal control law for my entire optimal control problem, then that optimal control law also needs to be optimal for each single one of these to-go problems. Because if it wasn't, then I could just switch to K to go, and then I can get a better overall cost, which means that my original proposed optimal controller wasn't optimal. Okay? So if this wasn't true, we would kind of get some contradictions arising. All right? So just as a side note, this is due to Richard E. Bellman. Okay, this is sometimes referred to as Bellman's principle of optimality. And if you're watching this and you're a PhD student, Bellman got his PhD in around 3 months. Okay, so if you're ever concerned about your progress, try not to think about Richard Bellman because he's a pretty sharp guy. All right. So with that said, let's kind of continue. Okay, so what this principle of optimality does is it kind of suggests a strategy for solving optimal control problems. Okay, so what we're going to do is, since we know that our optimal control law for our full system needs to be optimal for each of these to-go problems, let's try solving each to-go problem, and using the solutions to reconstruct an optimal solution for our full problem. Okay? So we'll kind of work backwards, right? We'll start with these smaller to-go problems. We'll kind of piece together solutions for each of these. And then maybe by this principle of optimality, what we'll end up with is an optimal control law for our entire system, okay? For our full optimal control problem, all right? So let's kind of start laying down some of the basic mathematical foundations for this, all right? First, what I'm going to do is I'm just going to define something called the optimal cost to go function, which just tells me what the best possible solution or the best possible value of this cost to go problem will be, okay? So let's say definition, this is the cost to go function. So just as a quick side note, this is sometimes also called the value function, all right? So this name value function is kind of more popular in reinforcement learning, all right? And we'll see it kind of pop up there. Okay, so let's say consider discrete time basic linear optimal control problem with horizon n greater than or equal to 0, okay? Now we say that the optimal cost to go function is a map J star, okay? I'm just going to take in two inputs. It's going to go from my state space Rn crossed with my time interval 0, n, and it's going to go to the positive reals r greater than or equal to 0. And it's going to be defined such that J star of x, m is equal to the infimum over u going from m up until n minus 1, x going from m up until n of my cost function, gn of xn, plus the sum term, which is just the usual sum. But now we're going from k equals m up until n minus 1 of g of xk, uk, k, and is going to be subject to x at time m equals the input x to this function, and x at time k plus 1 equals axk plus buk, right? And of course, these are going to satisfy the following subset of u and subset of Rn. Okay? So my cost to go function is simply going to be the optimal value of the optimization problem from state x if I had started at time m instead of at time 0. Okay? So this is kind of a piece of what we were talking about above, right? Which says that, all right, if we were able to go ahead and figure out this optimal cost to go, then maybe we could find a controller that achieves that optimal cost to go, and we could piece each of these controllers together to figure out an optimal controller for our entire optimal control problem. Okay? So how do we actually solve for this cost to go function? Right? Is there any kind of canonical strategy? Because it just kind of seems like we've just rewritten our problem, right? All that we've done is we've just taken the load off from one kind of complex optimization problem to another, right? Kind of seems like if we wanted to work our way back to an actual solution, we would need the optimal cost to go from time 0, and that's just equal to our original problem, right? So let's kind of see if we can make some progress on the relationship between these cost to go functions, right? Let's see if we can figure out if there's any kind of tricks that tell us how one optimal cost to go is related to another, okay? Let me just add an optimal cost to go. There we go. That was non-optimal spacing over there. All right. So let's figure out how we can solve for this. Let's start by solving for the optimal cost to go at step m equals n, right? All the way to the end. Because what this definition is telling us, right, is that the further we go into our horizon, kind of the easier this problem will be, right? Because the number of variables shrinks down, the cost function kind of simplifies, and so on and so forth, right? So if we're to go ahead and write down our optimal cost to go at time n, what we'll find is that j of x comma n is just exactly equal to gn of x, right? Because our entire accumulated cost term disappears, right? That sum term vanishes because we're at time step n, and all that's left is the terminal cost, okay? So this is just equal to the terminal cost. All right, so that's nice and easy, right? What else can we find? Well, our next simplest problem is back at step n minus 1, okay? So next easiest is at step n minus 1, okay? So what's j star of x comma n minus 1 equal to? Well, this is equal to an infimum over an input u, which I'll just say is an input u at time n minus 1. And our cost function is going to have two terms in it, right? It's first going to have the terminal cost term, right? Gn of x at time n. And then we're going to have one term, right? The loss term from the sum up here. So it's going to equal to this plus g of x at time n minus 1. There we go. U at time n minus 1 and n minus 1. This is subject to the constraints of x at n minus 1 equals x, right? The input to my optimal cost to go. And x at k plus 1 is equal to ax of k plus bu of k. All right? Let's kind of reorganize this cost function and see what we can tell, right? First, what I'm going to do is I'm going to just kind of substitute these constraints into the objective, right? That way we could eliminate the constraints. So everywhere I see xn minus 1, I'm going to put an x. And everywhere I see kind of an xk plus 1 looking thing, I'll put in this axk plus buk, all right? So when I do this, this becomes an infimum over un minus 1 of gn of x at time n, which is equal to a times x at time n minus 1, which is equal to x, right? Plus b times u at time n minus 1, okay? It's going to equal to that plus gx n minus 1 u n minus 1, n minus 1. Okay? Now, what do I notice? Well, what we had said above is that this gn term is equal to the optimal cost to go at time n, right? So I could also rewrite this as inf over un minus 1, which belongs to u, of, let me add a u over there. Forgive my shorthand. I'm just going to go ahead and put the stage cost first, just for ease. G of x n minus 1, which is just equal to x, u at n minus 1, n minus 1, plus gn of ax plus bu n minus 1, which we just said was equal to the optimal cost to go, j star at n. Okay? So what do we notice from this? So one is we notice a recursive relationship between j at n minus 1 and j star at n, right? They kind of appear on both sides, one with the dynamics plugged in. Right? And that's kind of interesting, right? Now, what else do we have? Well, we have a single variable optimization problem, right? So only need to solve for a single input. Okay, so that's pretty nice, right? We don't need to solve for some whole horizon. We can just solve for a single input. Okay, so, since that optimization problem is maybe not so bad, let's imagine that we were able to solve it, okay? So suppose we were able to compute this infimum for all values of x, and we can actually figure out j star of x n minus 1. Let's go back another step. Go back to n minus 2, all right? Now what's j star x n minus 2? J star of x comma n minus 2 for an arbitrary x is equal to the infimum over u at time n minus 2, u at n minus 1, where both of these belong to my set u. Now we're going to have a couple more terms, right? We're going to have this gn of x at time n term plus g x n minus 1, u n minus 1, n minus 1, plus g x n minus 2, u n minus 2, n minus 2, right? So we're also going to be optimizing over x going from n minus 2 up until n. It's going to be subject to x n minus 2 equals x, and then xk plus 1 equals axk plus buk, right? So things are kind of starting to look like they're complicating a little bit, right? A little tough. So what can we do to actually simplify this problem? Well, something interesting that we notice up here is that this guy, right, that kind of looks like what we were minimizing in the step above, right? So then the idea is, since we recognize this cost, which we were just trying to minimize in the step above, we can apply the principle of optimality, okay? Which says that if I have a control policy that's optimal for n minus 2, that also needs to be optimal for n minus 1, right? By this idea of this principle of optimality, where if you have something that's optimal for a whole problem, it needs to be optimal for a subproblem, right? So what the principle of optimality tells us is that if we're trying to solve this minimization, right, this term up here should need to match the optimal value for the n minus 1 problem. But what's the optimal value for the n minus 1 problem? Well, it's j star n minus 1, right? So this term is in fact exactly equal to the infimum over g x n minus 2, which is just equal to x, right? So I'll substitute that in. U n minus 2, n minus 2, plus my optimal value at n minus 1, right, by the principle of optimality. So this is going to be j star at x n minus 1, comma n minus 1, right? So this is going to be over u n minus 2, and then an x n minus 1, subject to AXK plus BUK equals XK plus 1, okay? But now what I'll do is I'll just go ahead and plug in for xn minus 1. And what I find is that this is equal to the infimum over un minus 2 belonging to u of g of x un minus 2 n minus 2 plus j star of ax plus bu n minus 2 n minus 1, okay? So what do I find from this? Well, what I get, another single variable optimization, right? So what we had started out with was a bunch of variables, right? We had a un minus 2, un minus 1, and a couple of values of x, right? Now what we found is that by applying the principle of optimality, which says that an optimal solution for n minus 2 also needs to be optimal for n minus 1, which is a smaller subproblem, right? By applying this principle of optimality, we were able to just substitute in our optimal cost to go from our previous time step, right? Once we did this, we just pop our constraint in. We find ourselves with a single variable optimization problem, right? Since the previous time step, we already determined the best thing to do at time n minus 1, okay? So this is a really powerful idea, okay? So this pattern kind of continues, and you get a recursive relationship, which will effectively tell you j star of x n minus, let me just call it m actually, j star x comma m is equal to the infimum over u, which belongs to your input set u, of g of x u m plus j star at your next step, okay? ax plus bu m plus 1, okay? So this kind of establishes this nice recursive pattern between these optimal cost to go functions, right? What this effectively tells us is that if we're able to solve for each kind of optimal cost to go, we can get the next one kind of recursively, right? If we're able to kind of keep solving these recursive optimization problems, maybe we could work our way down to solving our optimization problem for our full system, okay? So I will just remark, this needs a formal proof, okay? Needs a formal proof, okay? So in the case where the infimum is achieved, the argument is fairly straightforward, okay? But in the other case where the infimum isn't actually achieved, right, where there's not actually an input in your set u, which gives you precisely your infimum, the argument's a little bit more subtle, and you kind of need to do like an inequality in both direction kind of argument, okay? So the proof of that will be in the notes, but if you just want to kind of reason about it using this kind of simple structure that we had up here, where you just take the principle of optimality as a fact and you don't prove it, that's fine for the purposes of this course, okay, since we're not an optimal control class. All right, so let me go ahead and kind of state the results of what we set up here as a theorem, okay? So it turns out this basic recursion, which we just derived, underlies the method of dynamic programming, right? So what we've just shown is that by going ahead and solving each of these recurrences, right, we can solve a sequence of single variable optimization problems, which eventually will give us the solution of our overall dynamic optimization problem, all right? So let's state this as a theorem, which is dynamic programming. And we'll say consider a discrete time basic linear optimal control problem with horizon n greater than or equal to 0, okay? Then each step of the backwards recursion, remember it's a backwards recursion because we start all the way at the terminal state and we kind of work our way backwards, right? Backwards recursion, jn of x equals gn of x, where gn is our terminal cost, and jm of x equal to the infimum over in u of g of x m plus jm plus 1 of our dynamics, ax plus b times u times step m. Yep, that's it. Satisfy the following, okay? So this recurrence is such that jm of x equals the optimal cost to go, j star of x comma m for all x in Rn, and then m belonging to this interval 0 comma n. Okay, so what we're effectively saying is that our claim above, which is by the principle of optimality, this kind of recurrence should hold. This claim is in fact true, right? If we go ahead and we figure out what this recurrence is, we will in fact precisely get our optimal cost to go. All right. So there's a couple really nice consequences of this. So what we have is that consequently, two things. So one, we can find the optimal value. Okay. So what we have is that for all x naught in Rn, the optimal value of the optimal control problem is j star of x naught equal to this j naught of x naught, right? Where j naught is the last term in our recurrence. And the proof of this is essentially just based on the fact that your optimal cost to go starting from step 0 is equal to your optimal value, right? And if we're claiming that j0 needs to equal j star of x comma 0, then this result kind of follows directly from that. Okay? So first, what we claim is we can compute the optimal value from this recurrence, right? Now second, we say that we can actually get an optimal control law as well. Okay? So what are we going to say about an optimal control law? Well, if there exists a map K, which goes from your state space Rn, crossed with the interval 0, n minus 1, going into your input value space U, such that K achieves the infimum for all x and m. Okay, so for each m, K is going to achieve this infimum, which we defined up here. Then what can we say about K? Well, we can say K is an optimal control law. All right, and the proof of this is effectively that K is a map that's a function of state and time, which is achieving the optimal value at every single step. Okay, so as a result of this, K must be an optimal control law. All right, so the proof is similar to the recursion idea sketched out above. So this formally proceeds by induction. Okay, but you have to be a little bit careful here. The induction actually goes backwards, right, rather than forwards, since our recursion is going backwards. So you have a base case of n, and then you inductively go backwards, okay, until you get to your step 0. All right, so similar to the above, and once again, you need to be careful for case where the infimum is not achieved. Okay, so see the details in the notes. All right, nice. So this is the basic principle of dynamic programming. By solving for each optimal cost to go function and identifying a closed loop optimal control law at each step, we can reconstruct the optimal value of our full problem, right? And we can also reconstruct an optimal control law for our full problem. All right, fantastic. So this is the basic idea of dynamic programming. This is a really nice strategy for solving these basic linear optimal control problems which we highlighted. Now, since we're kind of short on time, I'm only going to spend a very brief amount of time kind of discussing the continuous time case, all right? But I just kind of want to state a couple of key results so you get a feel for what it's like. All right, so this goes ahead and brings us to the third part of our lecture, which is the Hamilton-Jacobi Bellman equation. All right. So let's quickly discuss what worked well about this discrete time case. What we were able to do is we were able to take this dynamic optimization problem and split it up into a sequence of static optimization problems, in each of which we were only solving for a single variable. All right? This was really nice. So what we want to do now is we want to come up with a method in continuous time for solving for for splitting up our problem, our dynamic problem into a set of static problems. Now this is especially difficult in this continuous time case, right? Let's just go ahead and rewrite out what this continuous time optimal control problem was, right? What we wanted to do is, if I just roughly sketch out, what the cost of my function was, an inf gt of xt plus the integral from 0 to t of g of x of tau, u of tau, tau d tau, such that x dot equals ax plus bu, and x of 0 equals x naught, right? Where now I'm performing an optimization over an input signal, u, right? So not just discrete values, but an actual signal in a function space, right? And also over a continuous function x from R to R. Right? Okay, so this is a much harder problem to solve. So much harder than the discrete time case, okay? Because we're performing an optimization in a function space. Okay, so this is an infinite dimensional optimization problem as opposed to the previous one. So what are we going to do? Well, let's kind of see if we could follow the same basic structure that we did in the discrete time case. All right. First, I'm just going to go ahead and define a continuous time optimal cost to go. Right. So this brings us to the definition, which is the continuous time optimal cost to go. So given one of these basic continuous time problems, we're going to define this as the map J star going from two arguments. Again, we have a state in Rn plus now an interval in R, 0, t. We're mapping to R greater than or equal to 0. This is defined as J star of x, t is equal to the infimum above, gt of xt, x of t plus the integral going from now time t up until t, g of x of tau, u of tau, tau, d tau, subject to x dot equals ax plus bu. Let me actually write an of t here so we don't confuse it with the other one. Ax of t plus bu of t. And x at time t is simply equal to x, right? Yeah, I have some conflicting notation here. Let's make this a tau. There we go. Tau, u of tau. All right, that looks better, okay? So this is, of course, subject to u and u and x continuous, okay? So this is our continuous time optimal cost to go, right? We're now saying, okay, if we start our problem at time t and from initial state x, what's the best possible cost that we can get out of that remaining optimal control problem? This looks kind of similar, right? If we go ahead and apply the same principle of optimality, what we'll find is that, if we pick a pair of times, t, which is less than or equal to some t plus a delta t, which I'll just call delta, which is less than or equal to my entire horizon, what I should find, right, is that j star of x, t is equal to the infimum over u of the integral going from t up until time t plus delta, g of x of tau, u of tau, tau, d tau, plus my optimal cost to go starting at x of t plus tau, right? T plus delta, okay? So this is what we should find, okay? So this is in fact true, all right? You can kind of show this. The reason is that your optimal cost to go starting from x and t should be optimal on t and t plus delta, and then it's going to be optimal on t plus delta until the end, okay? So we still have the same sort of idea as before, which, even though we're now in continuous time, what we're saying is that if you have something that's optimal from t all the way until the end, then that also needs to be optimal for every single subproblem, right? And that's where this, where this j star from t plus delta comes in. Okay, it tells us that whatever we're doing from t until the end needs to be optimal from t plus delta until the end. Okay, so this is this continuous time principle of optimality, right? And this kind of mimics this recursive relationship that we had said earlier, but there's a couple of kind of holes with this that you might tell, right? So this is still an infinite dimensional problem. And is still dynamic, right? This still involves our trajectory x of t, which is embedded in there, right? This is still the solution to a differential equation. So the main insight into the continuous time case is to get a static optimization problem instead of considering j star of x comma t and j star of x of t plus delta, what you do is you consider the time derivative of j star of x comma t along an optimal trajectory. Okay? So basically, the continuous time analog of just taking one step back is taking the time derivative, okay? So instead of moving one time step, like we did in this discrete time case, what we're doing is we're saying, okay, we're going to take the time derivative, and using this time derivative, we'll be able to get a static optimization problem that doesn't involve any trajectories whatsoever, okay? So basically what you'll find is using the continuous time optimal cost to go plus the principle of optimality. Oop, I used the wrong principle there. My gosh. Principle of optimality. What you'll find is that you can actually derive the following necessary condition on your optimal cost to go j. You'll find that for any x and t pair, the gradient with respect to t of j star of x comma t is equal to the minus infimum over u belonging to your input value space u. Okay, so this is not a signal anymore. This is just a single value of g of x at time t, u and t, plus the gradient with respect to x of j star of x comma t multiplied by ax plus bu. Okay? So basically what you'll find is that if you take this infinitesimal case, right, if you shrink it down to an arbitrary small amount of time, the principle of optimality will become this, okay? So this is a partial differential equation referred to as the HJB equation, or Hamilton-Jacobi-Bellman equation, all right? So unfortunately, we don't have the time to kind of go through a rough derivation of this in the notes today, or excuse me, in lecture today, but I'll include one of the notes and you can take a look if you're interested, okay? Basically, all this consists of doing is just taking this formula over here and just doing Taylor approximations and kind of substituting everything in and taking the limit as this delta goes to 0. We find that in the infinitesimal case, when delta goes to 0, this condition falls out, all right? Okay. So let me go ahead and state one final theorem, which just says, okay, this HJB equation actually works, and it gives us what we want, okay? This brings me to the final theorem, which is HJB equation. Okay, so what I'm going to say is consider a continuous time basic linear optimal control problem with horizon t greater than or equal to 0, okay? Let's say, suppose there exists a function v, going to take in 2 arguments. It's going to be continuously differentiable from Rn cross R into R, satisfying the Hamilton-Jacobi-Bellman equation. Okay, so it satisfies the gradient with respect to t, v of x comma t equals minus infimum over a static value, u and u, which is a subset of Rm. Okay, this is no longer a function space of g of x u t plus the gradient with respect to x, v of x comma t, multiplied by ax plus bu. Okay, so let's suppose v satisfies this. Let's suppose also that it satisfies the boundary condition v of t comma x equals the terminal cost, v of gt of x. Okay, so I'll come back and discuss these in just a sec. Okay, so let's say that this needs to hold for all pairs of x and t. All right, this function is continuously differentiable, and we get that it satisfies this nice HJB partial differential equation. What does this actually give us? Well, let's say, suppose there exists a continuously differentiable function, which I'll call k star, goes from Rn crossed with 0 comma t into u, which actually attains the infimum. The infimum above for all pairs of x and t. Then what can we say? Then we could say v is in fact equal to the optimal cost to go, which is j star, and the control law k star is optimal. Okay? So basically what we find is a direct analog of this dynamic programming algorithm in continuous time. Okay? So what we've done is we've replaced our terminal constraint condition in discrete time, which says that, all the way at the start of our recursion, we have, right, jn of x comma t equals this nice new function over here. Oops, I've got my arguments reversed. Should be, this should be a x, and that should be a t. Let me add this highlighter back. Okay. So now in place of this, start of the recursion, we have this boundary condition on a partial differential equation, which specifies, okay, all the way at the end at time t. My gosh, I did it again. There we go. That's better. All the way at the end, this function v needs to equal the terminal cost, and then instead of our recursion, we now have this derivative condition in time, which you can think of as kind of this dynamic programming recursion made infinitesimally small. We specify that the gradient in time of v needs to satisfy this infimum property over here. Okay? So if we can identify a function doing this, and we can identify a control law k, which actually achieves this infimum, then we can find an optimal control law for our system. Okay? So I know today we kind of kept things pretty high level. In the next lecture, where we discuss LQR, we'll see exactly how each of these things, both dynamic programming and the HJB equation, are actually used. Okay? So things will become a lot more concrete, and I think we'll get a good feel for how these objects actually work in practice. All right. Thanks for watching.